To introduce transformations, I want to remind you of what you know about using the substitution rule in single variable calculus. If we have an integral from 0 to the square root of pi of the sine of x squared times 2x dx, then we would identify that u is equal to x squared, and so du is equal to 2x dx. Under this transformation, we're transforming from x to u. The interval changes. Originally, x goes from 0 to the square root of pi, but under the transformation u equals x squared, u would go from 0 to pi. What we've done is we've changed the length of the interval, right? Another way to say that, though, is that we changed the shape of the interval. It's difficult to conceptualize shape when we're talking about a one-dimensional thing, but that's where we're heading in this series of videos. Now, to continue on with this example here, if we were to solve for 2x, we would end up with 2x is equal to du over dx, but now we really have a derivative notation. And this integral would become the integral of the sine of u of x. And if we're borrowing basically chain rule notation, we have the integral of sine of u of x du dx times dx, where du dx is actually represented by 2x. I know this is getting a little bit out there, but here's what we've got for this series of videos. The region over which we are integrating will change shape. In this example, it was x went from 0 to the square root of pi, and then u went from 0 to pi. We will have to do some work to find out what the analog is of what we have as du dx here, which you would have enacted using the substitution rule as saying that u is equal to 2x. That's background. Let's get into our current material. A transformation maps a region in R2 to another region in R2. It effectively changes the shape of a region over which we are integrating. Here we're talking about a double integral. The goal of this, usually, integrate over a simpler shape. I say usually because sometimes it's to convert the integrand, actually. Let's see an example that'll help us understand what transformations in R2 are about. Find the image of the set S under the given transformation. S is bounded by u equals 0, u equals 1, v equals 0, and v equals 1. The transformation is going to be from the uv plane to the xy plane. Transformation is denoted t here, and it's given as x is equal to v, y is equal to u times the quantity of 1 plus v squared. That squared is inside the parentheses. Before we see what this is going to look like, let's talk a little bit about the notation. The transformation t is really x, and we're thinking of it as x as a function of u and v, and then for something that's going to come in down the road here, we're going to call this g of uv. And then y is y as a function of u and v, and we're going to call that h of uv. Here's the point. X and y take in the ordered pair uv, and the result is something in the xy plane. So that's why we're saying the transformation takes something in the uv plane, those are the inputs, and gives us something in the xy plane because those are the outputs. We'll come back to that notion in a bit. Right now what we're going to do is we're going to see what happens to the boundaries u equals 0, u equals 1, v equals 0, and v equals 1 under the transformation that was given, which is x equals v and y equals u times 1 plus v squared. While we're at it here, let's go ahead and draw the region in the uv plane. We have four boundaries. V equals 0 goes along the u-axis. U equals 0 is along the v-axis. U equals 1 is a vertical segment. And v equals 1 is a horizontal segment. For good form here, I should say that this is the point 1, 1. This is 1 on the u-axis, 1 on the v-axis. And this here that we've just drawn, this 1 by 1 square, is the region S. Our goal here, and what the instructions say, are to find out what this region looks like under the transformation that's given. Let's take these one at a time. For v is equal to 0, Since x is equal to v, we have that x is equal to 0. And since y is equal to u times 1 plus v squared, if v is 0, we end up with y is equal to u. Based on the boundaries that we have, we know that u goes from 0 to 1. Therefore, y goes from 0 to 1. Now let's consider what happens to the boundary u equals 1. Since we know that x is equal to v, if u is equal to 1, then y becomes 1 plus v squared. And the result of those two combined is that y equals 1 plus x squared. Since x is v and we know that v goes from 0 to 1, we know that x goes from 0 to 1. For the boundary v equals 1, since x is v, we have that x is equal to 1. Y being u times 1 plus v squared, if v is 1, means that y is equal to 2u. Since, again, u goes from 0 to 1, we now know that y will go from 0 to 2. If I'm going to be consistent with my notation here, for the first one, I should draw a little arrow leading to y going from 0 to 1. That's for v equals 0. All right, last one. For u equals 0, we have that x is equal to v and y is equal to 0 because y has u as a factor, which means that since v goes from 0 to 1, x goes from 0 to 1. I'm going to rearrange these just a little bit so that I can make room for a graph over here. Let's see what happens to these boundary segments, because understanding what happens to a boundary tells us what happens to a region, in this case the region S. The boundary v equals 0 maps to x equals 0, and then y goes from 0 to 1. That is along the y-axis from 0 to 1. So this blue here maps to this blue here. The green segment here, u equals 1, maps to part of the parabola y equals 1 plus x squared, where x goes from 0 to 1. Folks, that's going to be an arc that looks about like this. It's just a piece of a parabola there. This purple segment up here at y equals 1, or at v equals 1, excuse me, is going to map to a vertical segment where x equals 1 and y goes from 0 to 2. And then this orange segment along the v-axis where u equals 0 is going to map to y equals 0 and x goes from 0 to 1. And so it's this horizontal segment along the x-axis. We've just learned that the transformation T maps S, a square region, into a square region in the UV plane. I don't want to leave that out. Into this region bounded by three line segments and the arc of a parabola. We're going to call that region R, and it's in the XY plane. That's the nature of a transformation.